Hello there and welcome back to The Sleepless Scientist. You're floating in a place that shouldn't exist. Not really. Not in the way we think of places. Around you is nothing, and not the cozy kind of nothing either. This is the raw, unprocessed void. No stars, no planets, no cute background nebula. It's colder than cold, quieter than silence, and yet somehow brimming with unspeakable tension. Because in a heartbeat, or less, this nothingness is going to turn into everything. You probably won't survive this, just saying. A blinding flash. The rules of physics punch into reality like a software update crashing onto an empty hard drive. The Big Bang. Not an explosion in space, but an explosion of space. Hotter than 1 trillion suns stacked into a single dot, and angrier than a toddler woken from a nap. You're there, somehow watching it happen, swaddled in the sheer absurdity of being alive in a moment that forged all the atoms that would ever exist. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop your current location and local time in the comments. I love seeing how far across space-time we've stretched. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. At first, everything is too hot for anything like atoms or matter. You can't even form a proton yet. It's all energy, like the universe started as one giant espresso shot of physics. But then, almost immediately, things cool just enough for particles to start crystallizing out of the quantum soup. Tiny things, quarks, gluons, electrons. They pop into existence like digital confetti. But here's the twist. Each of them appears with a partner, a dark twin, a nemesis made from the same cosmic cloth but wearing its label backward. For every particle, there's an antiparticle. This isn't a cute design quirk, it's fundamental. Matter and antimatter are born together, with matching masses and opposite charges. They're like perfectly choreographed dancers. One twirls clockwise, the other counterclockwise, and neither can touch without obliterating both in a flash of gamma light. And you might be wondering, why? Why bother spawning a universe in perfect pairs just to have them cancel out? Good question. Hold on to that. As you float through this subatomic storm, you see quarks zipping around with their antiquark shadows. Photons explode from annihilations faster than you can blink. The universe, not even a second old, is locked in a violent strobe of creation and destruction. Think of it as the world's worst popcorn machine. Each kernel that pops immediately explodes. But then, in the tiniest of imbalances, something shifts. For every billion antimatter particles, there's one extra matter particle. Just one. It's like the universe sneezed and forgot to clean up a few specks of dust. But those leftover specks, they're you. They're everything. Every star, planet, llama, baguette, and Taylor Swift album. All made from the survivors of a near-complete self-cancellation. And here's the kicker. According to our best models, that imbalance shouldn't have happened. The laws of physics, at least the pretty ones you learned in high school, say the Big Bang should have made equal amounts of matter and antimatter. Perfectly fair. Perfectly doomed. But it didn't. So now you're here, standing, or whatever the floating version of standing is, amid the fallout of that ancient mistake. You reach out toward the haze of the newborn cosmos, glowing pinkish gold like embers in a cosmic forge. Everything's expanding, stretching faster than the speed of light, and still somehow managing to keep its quantum secrets tucked under its sleeve. Historians, well, physicists, but we'll let them have their drama, still argue whether the laws of physics themselves played favourites, whether the universe cheated just a little in those first few trillionths of a second. A whisper of asymmetry, a preference for one spin direction over another, a fudge factor that led to you sipping tea on a Tuesday, instead of being a smear of radiation on a dark empty canvas. It's almost comical. The universe owes its existence to a rounding error. As you drift further, the forming universe becomes cooler, gentler, though still not exactly spa-day material. At around 1 second old, neutrons and protons start buddying up, forming the first hints of atomic nuclei. Photons, no longer instantly absorbed, begin to roam freely. It's the first whisper of light that won't be swallowed. And that light? It's still around today. It's called the cosmic microwave background, the CMB, a kind of baby picture of the universe, albeit one taken in thermal vision and covered in static. In the 1960s, two guys named Penzias and Wilson accidentally discovered it with a giant horn antenna and spent weeks trying to clean pigeon poop off their instruments, thinking it was interference. Turns out it was the echo of the Big Bang still murmuring across the cosmos. But even that light carries a secret. It's a universe built from matter. No clear signs of antimatter galaxies. No widespread annihilation zones. That slight imbalance, 1 in a billion, is the fingerprint stamped across all of it. Some theorists like to play with the idea that there could be entire antimatter galaxies out there, hiding in deep space, just out of reach. But we'll get to that later. For now, you rest inside the warmth of that improbable moment when everything that should have cancelled out didn't. A fun fringe theory from the 1970s proposed that matter and antimatter might be separated by giant domain walls, huge cosmic boundaries across which reality flips its sign like a vinyl record reversing. These walls, if they exist, should radiate in gamma flashes where matter and antimatter meet. Spoiler, we haven't found any yet, but they make for excellent sci-fi plots. And still, the question burns. Why the imbalance? What tipped the scales? You drift through the aftermath of that first second, surrounded by stardust that hasn't yet realised it will become stars. You think about the math, the coincidences, the near-total annihilation that almost left behind a blank slate, and the 1 in a billion leftovers that became home. And somewhere, nestled between all those cosmic particles and ancient gamma rays, is the strange suspicion that the universe didn't quite follow the script. Or maybe the script had a typo. You're still floating through the young universe, but things have calmed slightly. Less screaming inferno, more simmering chaos. The matter that managed to survive the great mutual destruction has begun to coalesce. Very, very slowly. While the photons from all those early particle annihilations are stretching into longer wavelengths as space expands. But you're not here for the peaceful leftovers. You're here to meet a ghost, or rather, an entire family of them. Imagine a mirror, not the kind hanging in your bathroom, but a quantum mirror. One that doesn't just reflect your shape, but rewrites your charge, flips your spin, and tells your entire existence to politely get wrecked. That's antimatter. Not evil, not cursed, just opposite. Like pineapple on pizza, it's perfectly valid, but some people insist it shouldn't exist. You watch, weightless, as particle-antiparticle pairs flash into existence. An electron appears, and alongside it, a positron. Same mass, same spin, but the positron has a positive charge instead of a negative one. You reach out to touch the pair, but they collide before you can get close. Instant flash, gamma radiation, gone. This dance happens 1 trillion times a second, in every cubic centimetre of that primordial soup. Particles and antiparticles twirling together for one final romantic disaster before they vanish in a puff of energy. It's beautiful if you're into high-speed fatal chemistry. The physics behind it is weirdly elegant. According to quantum field theory, particles are excitations in underlying fields, like ripples on a cosmic waterbed. Every known particle, electron, quark, muon, has a corresponding field, and those fields don't discriminate. They're perfectly happy to create both types of ripples, one for matter and one for antimatter, which means nature doesn't have a favourite, at least not on paper. But we've already established something's off. Something must have broken that symmetry, because we're here, you're here, and you're made entirely of matter, unless you've been lying about your particle content this whole time. You pass through the ghost of a neutron and catch a glimpse of what makes antiparticles so tricky. Let's say you have a particle travelling forward in time, in Feynman diagrams, those lovely scribbly charts physicists use to visualise quantum interactions. That particle's path is a simple arrow. But the antiparticle, it's drawn as the same type of particle moving backward in time. Yep, that's not just artistic flair. One interpretation of antimatter is that it's matter, but going the other direction through the timeline. No wonder physicists look tired all the time. Of course, that idea is debated. Historians, physicists, still argue whether antimatter truly represents time-reverse particles, or if that's just a clever math trick. But either way, it suggests that antimatter isn't just the opposite. It's the inversion of several fundamental qualities, possibly including time itself. You pause over a tiny blip of annihilation. 2 particles wink out of existence, a positron, an electron, just gone. And that's what makes antimatter so frustratingly dramatic. Every time a particle meets its opposite number, the universe gets a little flashier. They annihilate into energy, specifically photons, and those photons tend to be in the gamma ray range. Extremely high energy, extremely unfriendly. Which is why you don't want large amounts of matter and antimatter just hanging out together. It's not a rivalry, it's a guaranteed detonation. Now let's zoom in on that annihilation for a second. The particles don't just vanish. Their mass is converted entirely into energy, thanks to Einstein's handy little E equals mc squared. That equation isn't just something we slap on coffee mugs and t-shirts, it's the reason your antimatter sci-fi fantasies are so explosive. A gram of antimatter meeting a gram of matter would release energy equivalent to the Hiroshima bomb. Not a typo. 1 gram. A teaspoon of mutual obliteration. Suddenly that Star Trek warp core doesn't seem so far-fetched, except for one massive problem. We can't store antimatter, but we'll get there in due time. For now, you marvel at the scale of this dance. For every moment since the Big Bang, particles and antiparticles have flashed in and out of being. Even today, in the vacuum of space and the depths of particle accelerators, this cosmic tango continues. It's written into the very mathematics of the Standard Model. Our best, if deeply frustrating map of subatomic reality. And yet, no matter where you look, one truth remains. Antimatter is always outnumbered. Something about that imbalance doesn't sit right. You begin to wonder, what if the mirror version had won? What if you were made of antiparticles and thought that was normal? Quirky side note. In the 1940s, Soviet physicist Andrei Sakharov proposed that if you could somehow reverse the charge, parity and time direction of a particle, that's CPT symmetry, physics should look the same. Perfect mirror universes could theoretically exist and feel no different to their inhabitants. You, on the other hand, would look at an anti-you and immediately go, why is everything slightly sinister and glowing? But so far no anti-universe has RSVP'd, not even a postcard. Oh, and speaking of quirky, did you know that every time a banana decays, thanks to the potassium inside, it gives off a tiny bit of antimatter? Yep. Bananas emit positrons naturally. It's not dangerous, unless you're a banana with anxiety issues. Despite the sheer drama of matter-antimatter annihilation, this isn't just niche physics trivia, it's central to why anything exists at all. And it only gets weirder from here. You keep floating, watching the universe stretch into adolescence. Gravity starts pulling things into clumps, stars are still just a twinkle in the math, and antimatter, it's fading from the mainstream, relegated to whispers of radiation and lab experiments, like an ancient dynasty whose power has quietly slipped away. But in its heyday, antimatter wasn't just the universe's evil twin, it was its co-parent. It helped forge the laws of reality, challenge symmetry, and set the stage for the mystery at the heart of everything, why the scales tipped at all. You glance back metaphorically at those early pairings, those mirror-made lovers doomed to vanish, and you can't help but feel a pang of sympathy. They were born together, lived fast, died bright, and left behind just enough of a trace to make everything possible. You continue drifting, a spectator of the universe's adolescence, and something begins to nag at the back of your mind, some persistent itch beneath the smooth math and glowing plasma. You've seen the particle-antiparticle pairs, watched them blink into existence and flash out again in bursts of gamma light. You've witnessed the symmetry, the elegance, the balance. But where is it now? You're surrounded by stars and hydrogen clouds and endless glittering galaxies. All of it matter. Normal garden variety protons and electrons, No antiproton suburbs or positron nebulae in sight. It's like the universe cleaned up all the antimatter crumbs after a party and left no trace it was ever here. Suspiciously tidy, given how explosive things used to be. So, where did it all go? This, right here, is the cosmic vanishing act, the great antimatter disappearance, the mystery that, even today, keeps physicists pacing hallways at 3 a.m. with coffee in hand and wild ideas scribbled on whiteboards, because statistically speaking, the matter-dominated universe we live in shouldn't exist. It's like flipping a perfectly fair coin 1 billion times and getting matter every single toss. That's not a miracle. That's a rigged game or a broken coin. Let's rewind slightly. In that first microsecond of cosmic existence, we had perfect symmetry. For every quark, an antiquark. For every electron, a positron. Then the universe cooled just enough for them to start annihilating in spectacular mutual destruction. But for some reason, a tiny fraction, just 1 particle per billion, escaped that fate. And that tiny fraction, that's everything you now see. You, your pet, the moon, the weird smell in your fridge, all of it, built from the survivors of an extinction-level event that somehow missed a few outliers. No one knows why. Like truly, no one. This is the antimatter problem in its rawest form, and the technical name for it, baryon asymmetry of the universe, which sounds a little less dramatic than where the heck is all the antimatter, but that's science for you. The standard model of particle physics, the model that has predicted particle behavior with terrifying accuracy, doesn't explain this imbalance. It's like having a calculator that always gives the right answers but refuses to tell you how it got them. According to the rules we think are true, matter and antimatter should have wiped each other out entirely, leaving a blank universe filled only with radiation. But obviously, something tilted the scales. You float through the aftermath of that ancient imbalance, trying to picture what it looked like. Imagine watching 10 billion particles and antiparticles annihilate in quick succession, then realizing, with cosmic horror, that there are a few survivors still standing. Just a handful, but they're enough. More than enough. Now here's where things get twisty. Some physicists suggest that maybe the laws of physics aren't quite as symmetrical as they seem. That somewhere, buried in the equations, is a teeny, almost imperceptible bias. Like the universe had a favourite child and quietly slipped it a few extra cookies when no one was looking. And those cookies came in the form of matter. Particles that were ever so slightly more likely to stick around than their antimatter counterparts. That kind of rule breaking falls under the category of CP violation. We'll get to that more in a few sections, promise. But for now, just remember this. The universe might not be as impartial as it pretends. Some out there ideas even propose that antimatter isn't missing at all, it's just hiding. Somewhere, across the distant void, there might be antimatter galaxies, antimatter stars, maybe even antimatter life. That sounds wild, but we've looked hard. Telescopes like AMS on the International Space Station scan the cosmic rays constantly, searching for even one telltale sign of an anti-helium nucleus drifting through space. So far, nada, not even a whiff. And if there were large antimatter structures out there, we'd probably know. Wherever matter and antimatter touch, you get annihilation, and the gamma radiation it produces is unmissable. Think of it like a bug zapper the size of a solar system. If antimatter galaxies bumped up against matter galaxies, the edges would be glowing in high-energy light, and they're not even a little. Historians, well, you know the line by now, still argue whether the absence of antimatter signatures rules out entire anti-galaxies completely, or if we just haven't looked far enough. Maybe they're on the other side of the observable universe, keeping to themselves, muttering typical matter snobs under their breath. There's also the theory that antimatter was never evenly distributed in the first place. That maybe, for reasons we still don't understand, the very process of baryogenesis, the birth of matter, baked in a tiny preference, like a cosmic dice roll that kept landing just slightly off-center, favouring matter each time. Random? Maybe. But enough of those rolls, and you end up with a universe where one side got everything, and the other side got zilch. Another thought experiment. What if the missing antimatter is lurking in an alternate timeline or parallel universe? Okay, this one leans more sci-fi than physics journal, but it's not completely without merit. Some cosmological models suggest that the Big Bang could have birthed multiple bubbles of reality, some dominated by matter, others by antimatter. Think of it like cosmic patchwork. Our universe is one square on the quilt, stitched next to an antimatter square we can never quite see. And here's a charming fringe theory. Maybe the antimatter didn't disappear. Maybe we're the antimatter. The idea being that our labels are arbitrary, maybe what we call matter is just the version that survived, and if things had gone the other way, we'd be calling that matter instead. All based on which type happened to outnumber the other by that 1 in a billion margin. The universe doesn't care about our labels, it just went with the majority vote. Still, the mystery persists. We don't know why the balance tipped, we just know that it did. That somewhere between particle collisions and quantum fluctuations, the universe pulled off a sleight of hand trick that left behind only one kind of stuff. And you, dear sleepy traveller, are made of that lucky stuff. Matter, not antimatter. A universe built on the leftovers of a cosmic brawl, where one side mysteriously flinched. You drift past the remains of that ancient battlefield, now the building blocks of everything. You can almost feel the echo of what's missing, like the negative space in a painting. It's not just a technical curiosity, it's the central riddle of existence. Why is there something instead of nothing? And why did something win? You hover now in the cooling hush of the early universe, where protons and neutrons have stopped dodging annihilation and started cozying up to form the first atomic nuclei. It's still searing, still loud in its expansion, but there's a strange kind of calm setting in. The worst of the fireworks are over, but you're not here for the hydrogen cuddle puddles. You're back on the trail of the greatest imbalance in physics. You want answers. Why did matter win? The clue, it turns out, may lie in a few tiny, unspeakably subtle rule breakers, particles that violated what once seemed like sacred cosmic symmetry. You're now staring straight at what physicists call baryon asymmetry, the official name for the fact that matter outnumbered antimatter. This is the asymmetry that shouldn't exist. It's the smallest, most statistically offensive glitch in all of creation, and it changed everything. Now imagine this. You throw a perfectly balanced coin, not just once, but a trillion times, and somehow, every time, it lands matter side up. Not even a single antiparticle gets through. That's how improbably this universe should be. And yet here you are, made of quarks and leptons and a bunch of other zoo animals that all lean heavily toward matter. So how did we get this impossibly unbalanced outcome from what should have been a perfectly fair game? Cue one of the most eyebrow-raising concepts in modern physics, CP violation. That's short for charge parity violation, and it's exactly what it sounds like. A moment when the universe stopped playing fair. Let's break it down gently. Charge, C, means switching every particle's electric charge. A positive becomes negative and vice versa. Parity, P, means flipping the spatial coordinates, like turning the universe into its mirror image. And for a long time, physicists thought the laws of physics should remain the same even if you did both. Flip the charges, flip the mirror, same outcome. The universe should carry on, business as usual. But surprise, turns out sometimes that doesn't hold true. In 1964, physicists James Cronin and Val Fitch were messing around with kaons, those wonderfully unstable, misbehaving mesons, and noticed something peculiar. Some kaons were decaying in a way that violated CP symmetry. Basically, the particle and its antiparticle didn't behave the same in the mirror. One was ever so slightly more likely to decay into certain products than the other. That little discovery won them a Nobel Prize and shattered our illusion of a perfectly symmetrical universe. You imagine the moment standing beside them in the lab, eyes wide as they realize the implications. The laws of physics, biased. It's like catching your supposedly neutral referee handing a chocolate bar to one team before the game. And here's the kicker. This asymmetry, this CP violation, is one of the very few known ingredients that could explain why matter ended up beating antimatter. If the early universe allowed some particles to decay in slightly unbalanced ways, it might have tipped the scales just enough for matter to edge out. But don't get too excited yet. The amount of CP violation observed in kaons, and later in B mesons, isn't enough to fully explain the imbalance we see. It's like catching someone stealing pennies and realising millions are missing. There's a larger heist happening somewhere. Physicists still argue whether these small CP violations add up, or if there's a whole other mechanism we haven't even glimpsed yet. Some suspect that more exotic particles, long since decayed, held the real answers in those first moments after the Big Bang. Others believe neutrinos, those elusive ghost particles, may be up to something sneaky. More on them soon. Still, CP violation is one of our best suspects in this cosmic whodunit. It tells us that symmetry isn't a law, it's more of a suggestion. And speaking of symmetry, there's a lovely little idea called Sakharov's conditions, named after Andrei Sakharov, who laid out 3 necessary ingredients for matter to have triumphed over antimatter. 1. Baryon number violation. Particles need to be able to change from one type to another, violating the conservation of baryon number. 2. C and CP violation. You already know this one. The rules have to be unfair toward matter. 3. Departure from thermal equilibrium. The universe has to be in a chaotic, cooling phase where reactions can't all reverse. And wouldn't you know it, the early universe ticked all 3 boxes. A perfect storm of slightly wonky physics, drifting just far enough off script to leave a residue of matter behind. Like a baking recipe that calls for 1,000 grams of flour and 1,000 grams of water, but your kitchen scale is off by a gram and now you've accidentally made bread. But it's also possible, painfully possible, that there's more to the story. That the symmetry breaking we've observed is just the visible layer of a much deeper, darker truth. There's an entire family of speculative theories about grand unification, where the strong, weak and electromagnetic forces were once fused into one megaforce. During the cooling of the universe, that force split, and some of those phase transitions might have baked in the matter-antimatter asymmetry. Others take it further, like leptogenesis, which suggests that asymmetries among leptons, like neutrinos and electrons, played a key role, and those asymmetries later trickled down into the baryons, the heavier particles like protons and neutrons. Don't worry, you'll get a front row seat to the neutrino theories in a few sections. But here's a strange little fringe theory to chew on while you float. What if antimatter exists in our universe? Now, in perfect symmetry, but it's moving backward through time. According to one interpretation of quantum field theory, an antiparticle travelling forward in time is mathematically equivalent to a particle travelling backward. So maybe the antimatter is still here, just undoing our reality as we go forward. Which, if true, is the spiciest possible version of you can't see it, but trust me, it's there. You spin gently, surrounded by all this cosmic subtlety, and it hits you just how precarious your existence really is. One small tweak, one less CP violating decay, one more neutral phase, and the universe might have ended in darkness, or rather, never begun at all. Not in any form we'd recognise. And all this, from a particle that decided to misbehave just a little. So next time your toast falls butter side down, remember, at least it didn't annihilate in a perfect flash of symmetry. You live in an unfair universe, and that's why you're here. You're floating once more, not in the roiling chaos of the Big Bang, but in a quieter corner of the cosmos, where particles have calmed down, atoms have started behaving, and stars are just beginning to flicker into being. But you're not interested in ordinary hydrogen atoms or cheery plasma clouds. You're here for the weirdos, the twins, the mirror freaks of nature that every particle drags behind it like a guilty secret. Welcome to the inner circle of matter's evil twin, antimatter. Now, to be clear, antimatter isn't evil. It doesn't twirl a moustache or tie matter to train tracks. But it is, for lack of a better word, opposite. For every fundamental particle in the universe, protons, electrons, neutrons, even neutrinos, there's an antiparticle, equal in mass, but opposite in charge, and often reversed in quantum properties like spin. You watch one float by now, a positron, which is the antimatter version of the electron. It's dainty, positive, and dangerously polite. Introduce it to a regular electron, and they'll mutually obliterate in a blaze of gamma radiation. It's kind of poetic in a violent way. Then there's the antiproton, same mass as a proton, but with a negative charge. Combine it with a positron, and you get antihydrogen. Yes, the mirror version of the simplest atom. Same structure, same behaviour, and as far as anyone can tell, identical, except for those opposite charges. That's where things start getting deliciously eerie, because when you line up matter and antimatter, the universe should treat them the same. That's the idea behind CPT symmetry, the notion that if you flipped a particle's charge, C, flipped its mirror image, P, and reversed time, T, the physics would still hold up. But so far, real life keeps throwing up tiny violations, imperceptible nudges in behaviour, which is why we're still so obsessed with comparing matter to antimatter, checking whether its spin is just slightly off, whether it reacts to gravity the same way, whether it falls down in the same direction. Spoiler, no one is 100% sure yet. You reach out toward a glowing trail, an antimatter particle zipping through the vacuum of space. It's not a ghost, it's a real object, with real energy. But it doesn't play well with others. Antimatter is the loner kid in the particle playground. Everything it touches turns into light, which brings us to an important point: storage. In theory, antimatter is just as stable as matter. You could build an anti-U, with anti-atoms forming anti-molecules, forming anti-cells and anti-brains, and you get it. But you could never shake their hand. You'd both go up in smoke. Because that's the issue. We live in a matter-dominated universe. Antimatter doesn't have friends here. It's surrounded by enemies, and the moment it touches one, kaboom. That's why you can't just build an antimatter storage tank. The container itself, if made of matter, would instantly annihilate with the contents. So scientists get creative. They use magnetic traps to suspend antimatter particles in mid-air, keeping them isolated from any surface they might touch. It's like trying to keep a bubble from popping by, never letting it touch anything. Ever. There's a fringe anecdote for you. In the 1990s, NASA considered using antimatter as spacecraft fuel. The energy density is insane, 1 million times more than gasoline. But then they ran the numbers. It would cost about $100 billion to produce 1 milligram of antimatter, and you'd have to store it using magnetic fields in space, far from anything solid. As you might guess, the idea didn't make it past the napkin sketch phase, and yet, we do produce antimatter, every day, in tiny flickering quantities. Particle accelerators like CERN generate antiparticles all the time, especially antiprotons, by smashing protons into metal targets at near-light speeds. The energy of the collision transforms into particles and antiparticles, which can then be separated using magnetic fields. Even positrons pop up more often than you'd expect. In fact, your own body produces them. Yep, certain isotopes in your body emit positrons during radioactive decay. You're basically a walking, breathing positron factory, though the supply is tragically not enough to build your own warp drive. And, as bizarre as it sounds, there are even naturally occurring positron emissions in thunderstorms. Some scientists believe lightning generates intense electric fields capable of triggering gamma-ray bursts so strong they produce matter-antimatter pairs in the upper atmosphere. So next time you see a storm rolling in, just remember, there's a non-zero chance some of those clouds are chucking antimatter at the stratosphere. No biggie. But we're still stuck with the paradox. Antimatter is real. We've seen it, built it, studied it. But we've never found large chunks of it out in the universe. No antimatter planets, no antimatter stars, no signs of entire anti-galaxies colliding with ours in magnificent light shows. The skies are silent. Physicists have pushed our detection tools to the brink. We've set up detectors on satellites, in orbit, and even on the International Space Station. Instruments like the Alpha Magnetic Spectrometer are specifically designed to catch rare cosmic antimatter particles, and after years of scanning, we've found only hints, traces, never anything remotely suggesting a full-fledged antimatter region. So again, where did it go? Historians, I mean physicists, still argue whether some antimatter might survive in isolated pockets, far beyond our reach, perhaps hidden in the folds of dark matter, or in regions of the universe permanently out of communication with ours due to the expansion of space. But the more we look, the more lonely this universe appears. Just matter, as far as the eye can see. The antimatter, evicted, discarded, or maybe sacrificed. It's a little spooky, honestly. Like waking up to find the whole town deserted, every mirror shattered, and no one remembers what the reflections used to look like. Still, there's comfort in knowing the rules, however flawed, have kept us alive. Antimatter is beautiful, precise, poised, but also volatile, solitary and doomed in our particular corner of reality. You watch as a solitary antiproton drifts by, wrapped in a magnetic cocoon, caught by a lab on Earth 13.8 billion years after its kind lost the great cosmic race. It hums with energy, a relic of a symmetry that should have left nothing behind. And yet, here you are. You find yourself hovering beside a humming chamber of mist and glass, circa 1932 Southern California. The world's still figuring out how to tie its quantum shoelaces, and yet, in this small lab, something unthinkable is about to be caught red-handed in a puff of vapour. The chamber is called a cloud chamber, a sealed box filled with supersaturated alcohol vapour, and it's about to make physics history. Carl Anderson, a young physicist at Caltech, is studying the behaviour of cosmic rays, high-energy particles from space that bombard Earth constantly. He's not expecting to find anything new, just mapping the trails these particles leave as they streak through the mist, like jet contrails in miniature. You float beside him now, watching the trails snake and curve. Then it happens. A particle zips through the chamber and leaves a track, but something's off. The curvature of the path under a magnetic field is wrong, not just unusual, backward. The particle bends in the opposite direction to an electron, yet has the same mass, same shape, same behaviour, just opposite. Anderson doesn't know it yet, but he's just caught the positron, the first antimatter particle ever observed, and the first concrete proof that antimatter is real, not just a mathematical curiosity scribbled in the margins of a quantum textbook. You lean in close, watching the trail fade, delicate as a breath on cold glass. This little vapour squiggle is a revolution. Until now, antimatter had only existed in theory. The idea first popped up in the mind of Paul Dirac a few years earlier. He had been trying to combine quantum mechanics with Einstein's special relativity, because that's what you do when you're brilliant and bored. Dirac's equations predicted a particle exactly like the electron, but with opposite charge. At first, people thought this must be a mistake, or worse, a math ghost. Even Dirac didn't quite believe it. He hesitantly proposed that maybe it was the proton, which was already known, but didn't fit cleanly. Eventually, he accepted the uncomfortable truth. His math described a completely new kind of matter. And then Anderson found it, casually waltzing through a cloud chamber like it had always belonged. The discovery was so shocking that Anderson didn't immediately know what to call it. He briefly considered a negatron for the electron, since the new thing was positive, and positron for the newcomer. Thankfully, only one name stuck. You float around the chamber, admiring how one accidental discovery changed everything. Because now, antimatter wasn't just a concept. It had a face, a track, a place in the real world. The positron became the poster child for antimatter, and soon more antiparticles followed. Antiprotons were discovered in 1955 at Berkeley by Owen Chamberlain and Emilio Segre, using a particle accelerator called the Bevatron. Their discovery too won a Nobel Prize because apparently spotting antimatter is just what you do when you're trying to impress Stockholm. By the 1960s, physicists had built an entire zoo of particles and antiparticles. For every known member of the subatomic family, muons, pions, kaons, there was an evil twin. It was like unlocking the mirror realm in a video game and realizing the enemies look exactly like your character, but with moodier lighting and a taste for dramatic exits. But positrons still hold a special place, not just because they were the first antiparticles discovered, but because they're the most accessible. You've probably seen one today and didn't even realize it. If you've ever had a PET scan, that's positron emission tomography, you've relied on antimatter. It works like this. A radioactive tracer is injected into your body. It emits positrons, which immediately collide with electrons in your tissues. This causes annihilation, releasing pairs of gamma photons that zoom off in opposite directions. Detectors pick up the photons, and voila, you get a 3D image of your insides. It's like your body turns into a miniature collider. Not bad for something that once only existed in theory. And speaking of naturally occurring positrons, remember those bananas we talked about? Yeah, they're still doing it. Because of the potassium-40 inside, bananas emit about 15 positrons per day. It's not enough to give you superpowers or even a decent glow, but it's a cute party fact if you're ever stuck in an elevator with a physicist. You pass now into a quieter memory, a dusty corridor in a library, where a footnote in Dirac's early papers mentions something odd. He once speculated that the entire universe might be composed equally of electrons and positrons, separated by some unknown force. That's adorable and completely wrong. But in 1931, he had no way of knowing. Historians still argue whether Dirac truly understood the philosophical weight of his prediction, whether he knew that by writing down one simple equation, he had cracked open a mirror world, a world that would eventually lead to questions about the fate of the entire universe. And that's the strange beauty of it. The positron, just a single antiparticle, proved that the universe could produce matter and antimatter in equal measure, that it should be balanced. Which of course brings us back to the big, uncomfortable question, why isn't it? You leave the cloud chamber trailing behind a wisp of annihilation radiation and drift back into the cosmos, now armed with the knowledge that antimatter isn't hypothetical. It's here, it's detectable, it's just missing on a cosmic scale. The positron, after all, was just the beginning. A crack in the mirror that would eventually lead to entire labs being built to chase its siblings down. And as you watch the lab fade behind you, one more odd fact sticks in your mind. In 1933, Anderson also spotted something else in his cloud chambers. Another strange particle, one that didn't quite match anything yet known. It turned out to be the muon, the electron's heavier cousin. It wasn't antimatter, but it reminded physicists that the universe had layers, unexpected, unwelcome, deeply puzzling layers. And for every new layer we uncovered, the mystery deepened. You drift now through a cavernous chamber deep underground. The walls hum with electromagnetic precision, lasers blink their coded rhythms, and banks of monitors flicker like candlelight for the 21st century. Welcome to the frontier, modern antimatter production. You're in a lab, yes, but not just any lab. You're in the company of titans, institutions like CERN in Geneva, where physicists routinely conjure antimatter from collisions that mimic the intensity of early cosmic events. This isn't just science. It's an opera of particles meticulously staged and perilously expensive. Let's start with how they do it. Making antimatter sounds like something you'd need a wizard for, but it's essentially brute force physics. Take protons, speed them up to near light speed using a particle accelerator, then slam them into a metal target, usually tungsten or copper. The impact is so violent it tears space-time just enough to let energy condense into matter and antimatter. You peer into one of these collisions now. A high-energy proton strikes the target and suddenly, flash. Particles burst into being, including antiprotons. They last just fractions of a second before hitting something and annihilating. So the challenge isn't just making them, it's keeping them alive. That's where the real dance begins. The freshly created antiprotons are herded away from the chaos using magnetic fields. Like cats at a laser pointer convention, they're nudged into containment zones, special chambers where they can be slowed, cooled, and eventually trapped. Enter the Penning trap, a magnetic and electric field configuration designed to keep charged particles suspended in a vacuum. Antiprotons go here to chill out, literally. They're cooled using sympathetic techniques involving other particles until they're cold enough to handle. And by handle, we mean watch very closely and never touch. You glide into a quiet corner of the lab where another experiment buzzes with anticipation: antihydrogen production. This is where scientists combine positrons and antiprotons, two bitter cosmic X's, into a stable, neutral atom of antimatter. It's a painstaking process. If the particles approach each other too quickly, boom. If they touch the walls of the chamber, boom. If someone coughs near the magnet array, well, you get the idea. But sometimes, with the precision of 1,000 PhDs and more magnets than a fridge door in a Midwestern kitchen, it works. An antihydrogen atom forms and floats, trapped in a vacuum by pure magnetic trickery. You pause and marvel. That little atom is the antimatter version of hydrogen, the most common element in the universe. But this one is so rare, it costs thousands of hours and millions of dollars to make. If there were a black market for physics bling, this would be it. Now here's the twist. These labs don't make antimatter just to prove they can. They do it to ask questions, to test whether antimatter behaves exactly like matter. One big mystery. Does antimatter respond to gravity the same way? You'd think this would be obvious. Of course it falls down, but remember, we've never had enough antimatter to just drop it. Until recently. At CERN, the Alpha collaboration has been leading the charge. In 2022, they dropped antihydrogen atoms inside a magnetic vacuum chamber and watched what happened. The result? They fell down. Not dramatically, not up, but down. This was huge. It suggested that antimatter probably responds to gravity just like matter, but it wasn't precise enough to close the book. More experiments followed, alpha, G and base, to test if there are any subtle differences. Even the tiniest deviation would shake our understanding of general relativity and maybe, just maybe, point toward new physics. You hover above one of these experiments now. The antihydrogen floats like a ghostly pearl suspended by magnetism. The scientists are watching it fall with exquisite patience, looking for any signs of disobedience. So far, no rebellion. But physics loves a late plot twist. And here's the hilarious part. While we spend billions trying to create micrograms of antimatter, the universe casually throws it around for free. Cosmic rays from deep space crash into Earth's atmosphere every day, creating muons, pions, and yes, antiparticles. There's even a natural phenomenon called a terrestrial gamma-ray flash, where thunderstorms generate positrons in high-altitude lightning bursts. Antimatter, it turns out, isn't rare because it's impossible. It's rare because it doesn't last around matter. We can make it, we can measure it, but we can't hold on to it. It's the universe's most ephemeral substance, always one collision away from becoming a puff of light. You pass now through the legacy of failed antimatter storage ideas: metal containers, annihilation, glass chambers. Boom! Even electromagnetic traps struggle with neutral antimatter, like antihydrogen. The solution? Magnetic minimum neutral atom traps. Basically magnetic bottles where the magnetic moment of the atom keeps it suspended like a scared squirrel between two magnets. There's a fringe theory among amateur physicists, brace yourself, that if you could create a container made entirely of antimatter, you could store antimatter inside it safely. The only problem is, to build the container, you'd first need a container to hold the antimatter needed to build the container. It's the antimatter version of trying to pick yourself up by your shoelaces. Historians, come on, still argue whether it's even theoretically possible to produce enough antimatter to make anything useful, let alone store it without destroying the universe's most expensive science project. And yet, we keep trying. Because deep down we know antimatter is more than just a curiosity. It's a key, a tool, a mirror we can't stop staring into. You float one last time past a lab technician, adjusting the cooling lasers on a positron trap. Her face is calm, focused. There's a kind of reverence here, like watching someone balance a single snowflake on a pin. Because she knows what's at stake. This isn't just science, it's a conversation with the early universe, one antimatter atom at a time. And if we listen closely enough, the mirror might speak back. You're gliding now along a very different kind of path, not through a sterile lab or the primordial haze of the Big Bang, but down the flickering hallways of imagination. Welcome to the world of science fiction, where antimatter isn't delicately trapped behind lasers and magnetic coils. It's tossed around like a glorified AA battery. And hey, it makes sense, doesn't it? If antimatter is just matter's mirror image, with the same mass and way more pizzazz, then why not use it to power spaceships, blow up bad guys, or casually destroy a city block to prove a point? But before you get too cozy with your antimatter daydreams, let's do a little myth-busting. Because the truth is, antimatter is both more amazing and less convenient than fiction makes it out to be. Let's start with one of the flashiest examples, Angels and Demons. You remember, the Dan Brown novel and Tom Hanks movie, where the Vatican is under threat from a bomb powered by a few drops of antimatter. Sounds fun, right? Now here's the twist. The science in that story isn't entirely wrong. If you could somehow trap just 1 gram of antimatter, say antiprotons and positrons, and let it collide with a gram of matter, you'd release about 90 terajoules of energy. That's equivalent to the bomb dropped on Hiroshima. So yeah, terrifyingly powerful. But here's the thing. We've never produced anywhere close to a gram of antimatter, not even a milligram. In fact, in all of human history, we've made less than a few nanograms total. And to make just 1 nanogram, you'd need to run CERN's particle accelerators at full tilt for days, maybe weeks, and spend millions of dollars doing it. One physicist famously quipped, "Antimatter is the most expensive material on Earth," which is hilarious when you remember it vanishes the moment it touches literally anything. So, to all those sci-fi scenarios where villains casually store antimatter in metal tubes or glass orbs, sorry, but nope. That containment device would need to be a high-vacuum magnetic field generator capable of levitating charged particles indefinitely without letting them bump into anything, and it would probably weigh more than the spaceship it's supposedly powering. But still, what if? Let's give fiction its due. In Star Trek, antimatter is used as fuel for the warp core, where matter and antimatter annihilate in a controlled reaction chamber, producing energy to bend space-time and move faster than light. It's clean, efficient, and beautifully tidy. And while we're light years from warp drives, the concept isn't actually that ridiculous. In theory, antimatter could make the ultimate rocket fuel. Traditional rockets rely on chemical combustion, which is horribly inefficient and sluggish. Even nuclear rockets pale in comparison. But a matter-antimatter engine, that's peak energy output. Every ounce of fuel turned directly into energy. No waste, no residue. Just pure, glorious thrust. 1 gram of antimatter could, in theory, send a probe to Pluto in a matter of weeks. But then again, one sneeze in the wrong direction, and it's Pluto's problem now. Still, serious minds have played with this idea. NASA's Institute for Advanced Concepts has explored antimatter propulsion concepts, usually involving beams of antiprotons interacting with spacecraft fuel to create thrust. But these proposals always hit the same wall. We don't have the technology to produce or store antimatter safely, efficiently, or in useful quantities. It's like planning a barbecue when the nearest cow is on Mars. There are also some lovely fringe ideas out there. Some researchers once suggested using antimatter to trigger small-scale fusion reactions. Not to power the reaction directly, but to provide the spark that gets a fusion engine going. Think of antimatter as the world's most overkill lighter. And then there's the dream of the antimatter bomb. Let's get this out of the way. No, there is no stockpile of antimatter warheads hidden in Area 51. But yes, the military has looked into it. In the Cold War days, there were programs that studied whether antiprotons could be used to initiate fusion reactions, an antimatter trigger instead of a fission bomb. Fortunately, or unfortunately, depending on how you feel about civilization, this was way beyond our capabilities. Still is. But fiction doesn't care about feasibility. It cares about drama. In countless books, movies, and games, antimatter is the wild card. The rare fuel, the unstable core, the ticking time bomb. Sometimes, the depiction is shockingly accurate. In The Expanse, antimatter weapons are explained with almost frustrating realism, produced in tiny amounts, extremely unstable, and only used by the most advanced factions. In Mass Effect, the spaceships use matter-antimatter reactions, but they solve the containment problem with a fictional material called ESO. Convenient. Other times it's delightfully unhinged. In Doctor Who, entire universes run on antimatter, casually tucked away behind plot-proof force fields, and in Half-Life, let's not even try to explain how the antimass spectrometer works. Spoiler, it doesn't. But hey, even in fiction, antimatter holds a mirror to our reality. It's the ultimate example of something that's both extraordinarily powerful and maddeningly impractical. We know how it works. We can create it. But we can't tame it. Not yet. Oh, and here's a fun fringe fact for your late-night trivia bank. Some conspiracy theorists believe that UFOs are powered by antimatter engines. Yep. They argue that the US government has secretly mastered antimatter containment and uses it to fuel alien-style craft. Never mind the fact that we can barely store one atom at a time without a Nobel Prize committee watching. It's always aliens. Historians, no, this time actual historians, still debate how much influence early 20th century sci-fi had on the direction of antimatter research. Some believe that popular media helped drive funding and public interest, pushing labs to explore wild frontiers just to keep up with imagination. Which is a lovely way to say, sometimes science chases fiction. So now you float between fact and fantasy, watching positrons annihilate in medical devices while starships leap to warp on screen. Antimatter is both a miracle and a migraine. It's the cleanest energy source we can't use, the deadliest weapon we can't build, and the rarest substance we keep accidentally creating. In the end, antimatter may be less of a sci-fi prop and more of a cosmic lesson in patience. The universe handed us the blueprint for infinite power, and then said, cool. Now spend a few centuries figuring out how not to vaporize yourself. You're drifting now beyond the confines of labs, movies, and cloud chambers, deeper into your imagination. The rules of reality begin to shimmer at the edges, like heat waves on a desert road. Because tonight we're asking a question so bold it almost feels rude. What if the universe had gone the other way? What if antimatter had won? What if, instead of quarks and electrons taking over after the Big Bang, it was anti-quarks and positrons that pulled ahead? Would anything be different? Would physics collapse in protest? Would it feel different to walk on an anti-sidewalk, eat anti-toast, fall in anti-love? The short, disturbing answer, probably not. You blink and suddenly you're there, coasting through an alternate cosmos built entirely from antimatter. Stars sparkle just the same. Galaxies swirl in familiar Fibonacci spirals. Planets orbit suns. Comets trail behind them. And somewhere, in a quiet antimatter kitchen, an anti-cat knocks over an anti-glass of water out of pure spite. Because here's the thing, antimatter behaves almost exactly like matter. An antiproton and a proton, same mass, same stability. An positron and a regular electron. Again, same deal, just reverse charge. Put them together and you can form anti-atoms. Combine those into anti-molecules, and eventually into anti-chemistry, anti-DNA, and presumably, anti-people. If the Big Bang had left that 1 in a billion imbalance tilted the other way, the universe might look almost identical. Historians, physicists, still argue whether we'd even be able to tell the difference if we suddenly switched places with our mirror cousins. Maybe their physics textbooks are written in cursive. Who knows? But from a physics standpoint, everything would work just fine. Fusion would power stars, chemistry would build life, and awkward first dates would still end with someone pretending to get an urgent text. So why don't we see any of this antimatter structure out there? You float to the edge of a spiral galaxy and peek beyond, where the void stretches cold and black. If antimatter galaxies exist, if there were entire regions of the cosmos dominated by anti-atoms, we'd expect to see signs of it at the boundaries where antimatter and matter meet. That boundary would be absolute carnage. Every contact point would erupt in gamma-ray annihilation, the cosmic equivalent of fireworks on steroids. And yet no such signals have been found. The sky is quiet, suspiciously so. That's why many physicists now believe that if antimatter did form anti-galaxies, they'd have to be so far away, beyond our cosmic horizon, that we'll never see them. The expanding universe makes sure of that. It's like the cosmic version of long-distance relationship, doomed to silence forever. But here's where it gets even weirder. You don't need entire galaxies to imagine an anti-world, just an anti-planet, a rogue hunk of antimatter rock drifting somewhere in deep space. If it bumped into an asteroid made of matter, boom. If it dipped into a gas cloud, double boom. Yet again, we've looked hard. Instruments like the alpha magnetic spectrometer on the International Space Station scan cosmic rays for telltale signs of heavy antinuclei, like antihelium. If we ever found even one antihelium nucleus floating around in space, it would strongly suggest that somewhere out there, antimatter isn't extinct, it's just keeping to itself. So far, nada, just a few tantalizing events that may or may not have been cosmic rays playing tricks. Which leads to an uncomfortable possibility. Maybe you can't build a large structure out of antimatter, not because physics won't let you, but because the early universe was too violent, too chaotic, too biased. Maybe those earlier symmetries weren't just small bumps, they were structural. Maybe matter just clumped better. Maybe antimatter couldn't form stable regions before being annihilated away. Historians, yes, them again, still debate whether inflation, the rapid ballooning of space after the Big Bang, could have separated regions of matter and antimatter before they touched and destroyed each other. But if that's true, then those anti-regions would be so far apart they'd effectively be in separate universes, which would be poetic if you weren't so determined to meet your anti-self. And about that, your anti-self, the one made of positrons and antiprotons and whatever weird anti-thoughts they think. Well, let's pretend for a second they did exist and they'd be standing in their version of this very moment, maybe sipping anti-tea, possibly listening to an anti-sleep science podcast, pondering whether you exist. Which honestly makes this all feel a bit more romantic than it probably should. Because from their perspective, you're the anomaly. You're the shadow universe that somehow survived the Big Bang's great coin toss. You're the evidence that something, somewhere, didn't add up. There's an unsettling fringe idea that sometimes gets tossed around late at night in physics departments, that the laws of physics require a balance, that for every region of matter, there must be a region of antimatter, not to maintain symmetry exactly, but as part of a deeper conservation law. So if you're here, floating in a matter-dominated universe, maybe there's another version, elsewhere, filled with antimatter, and maybe that anti-world thinks it's the real one. Of course, there are problems. You couldn't bring a sample of antimatter into our world without destroying it, and us. Inter-universe travel, even if it existed, would be complicated by annihilation at every level. It'd be like trying to high-five your reflection through a brick wall, made of explosions. But let's dream anyway. What would an antimatter Earth look like? Pretty much the same. Trees, clouds, oceans, dogs chasing cats, TikToks, awkward weather reports. The chemistry would behave identically, the biology would hum along, and someone would still get upset that their coffee has too much milk. But if a single pebble from that world crossed into ours, it would unleash more energy than a nuclear bomb. In the end, you're left with a kind of bittersweet awe. An antimatter universe is entirely plausible. It could exist. It could even be watching us. But if it does, the two of you are destined never to meet. You drift back from this anti-fantasy into the safety of your overwhelmingly matter-based universe. Everything around you, your thoughts, your atoms, the screen you're listening through, is a product of that 1 in a billion imbalance after the Big Bang. So be kind to the mirror version of you. They didn't lose. They just got written into a chapter you'll never get to read. You're somewhere cold now, vast, silent. The kind of silence so complete it makes your ears ring. You've left behind laboratories and galaxies and fanciful mirror worlds. Out here, in the raw dark between the stars, is where the real search happens. Not for aliens, not for warp drives, but for something more elusive, evidence that antimatter still exists, out there. You drift alongside a sleek machine in low Earth orbit, the Alpha Magnetic Spectrometer, or AMS-02. It's been attached to the International Space Station since 2011, quietly combing through cosmic rays like an obsessive librarian looking for a single misfiled card. Its mission? Find heavy antimatter. Not positrons, we've seen plenty of those, but real nuclear-level stuff. Antihelium to be specific. Because here's the thing, if you ever find an antihelium nucleus floating through space, it's game over for the matter-only universe theory. You don't get antihelium from random energy blips. It's too big, too stable, it needs stars, it needs structure, it needs, brace yourself, an anti-galaxy. And if there are anti-galaxies, well, the entire narrative of cosmic evolution needs a rewrite. You hang close to AMS-02 as it sifts through particles, millions per day, sorting matter from antimatter by their charge and curvature through its magnetic field. Occasionally, a positron blips across its sensors, sometimes even antiprotons. These are expected, created when cosmic rays smash into particles in deep space. But antihelium? That's different. That's treasure. There have been a few suspicious events. Maybe signals that might be antihelium, but they're rare, fuzzy, hard to confirm. And physicists are famously skeptical. They'd rather spend a decade being unsure than 5 minutes being wrong. So AMS-02 keeps looking and waiting. You drift away, further into space now, toward the faint glow of distant stars. Some researchers have wondered if antimatter could survive out there, in the intergalactic voids between galaxy clusters. These are massive regions of near-nothingness, so empty you could fly 100 galaxies through them and never hit anything. Maybe, the theory goes, antimatter lurks in those cold corners. Maybe it was pushed there early on, segregated by inflation or expansion, and has been minding its own business ever since. After all, if antimatter and matter stayed far apart, they wouldn't annihilate. They'd just avoid each other. A cosmic cold war. But again, no signs, no gamma-ray bursts, no energy trails from annihilation. Just silence. You reach the rim of a galaxy now, not our own but 1 million light-years away. It swirls peacefully, blue-white arms arcing through the black. If antimatter galaxies existed, they'd look just like this. Because frustratingly, there's no visual difference between matter and antimatter. A galaxy of antiprotons and positrons would shine the same as one of protons and electrons. Same chemistry, same light. The only giveaway would be in the interactions, at the edges, where matter and antimatter meet. Those boundaries would glow with 511 kilo-electron volts gamma rays, the telltale signal of electron-positron annihilation. So scientists have mapped the sky in that energy range, hoping to spot a glowing fringe, a halo of gamma light where antimatter might be brushing up against us. Still nothing. Historians, and by now you're probably whispering this along with me, still argue whether the lack of annihilation signals definitively rules out large antimatter regions, or if we're just not looking in the right place. Maybe the gamma rays are drowned out by other cosmic noise. Maybe annihilation only happens in rare, unpredictable bursts. Or maybe, just maybe, antimatter never formed structures. It was wiped out too early, too completely. Left behind only as whisper traces in particle accelerators and positrons in thunderstorms. And yet something keeps you searching. There's another set of eyes on the sky. Fermi, a space-based gamma-ray observatory launched in 2008. It scans the universe for bursts of high-energy light, including the very frequencies that would signal annihilation, and it has seen some curious things. Mysterious gamma-ray structures near the centre of our galaxy, shaped like giant bubbles. They're called the Fermi bubbles, and no one really knows what caused them. Some think they're the relics of ancient black hole tantrums. Others wonder, quietly, cautiously, if there's any link to antimatter. Fringe theories abound. Some researchers have suggested the centre of our galaxy might contain antimatter clouds. Just enough to create interactions, not enough to survive as structures. But there's no smoking gun. No confirmed source, just more data, more noise. Meanwhile, back on Earth, detectors like BESS, Pamela and AMS continue to look for any heavy antiparticles. The logic is simple. If even one anticarbon nucleus is found, it's definitive proof of complex antimatter chemistry, which would mean, somewhere out there, matter didn't win everywhere. So far, still zilch. And yet you can't shake the thought, what if we're just a bit unlucky? What if the antimatter regions are out there, just beyond the observable universe? The part of space that's so far away, Light from it hasn't had time to reach us since the Big Bang. The universe could be vastly larger than what we see, possibly infinite. Maybe some far-flung sector, billions of light years away, got the other version of the dice roll. There's even a theory, mostly speculative but charming in its absurdity, that in an eternally inflating multiverse, each bubble universe could be matter or antimatter dominated. We just happen to be in a matter one. Somewhere else, anti-people are floating in their own anti-reality, scanning their skies and wondering why they've never seen an atom. You float back toward Earth now, surrounded by the constant hum of unanswered questions. We've built detectors on balloons, planes, satellites and space stations. We've scanned the skies for decades, and while we've seen fleeting hints, nothing's ever crossed the line into hard proof. Still, we keep looking. Because finding even one confirmed antimatter structure, a single anti-helium nucleus, would change everything. It would mean the antimatter isn't gone, it's just elsewhere, separated, preserved. And in a universe built on symmetry, that possibility is just too tempting to ignore. You're drifting now through something smaller than galaxies, quieter than deep space, and stranger than even antimatter's absence. You've left behind the star fields and satellite instruments to dive into the very handedness of the universe itself. That's right, today you're getting philosophical about left and right. Don't laugh. It might be the key to why anything exists at all. You hover now at the quantum level, where particles don't just move, they twist. Every fundamental particle carries something called spin, though it's not quite like a top spinning on a table. It's a quantum property, angular momentum without motion, like a reputation for dizziness. And this spin gives particles a sense of handedness, or chirality. Imagine watching a particle moving toward you while spinning. If it spins clockwise, it's right-handed. If it spins counterclockwise, it's left-handed. Simple, right? Here's where the weirdness kicks in. When it comes to the weak nuclear force, the universe plays favourites, and not subtle ones either. It absolutely despises right-handed particles. It only interacts with left-handed particles and right-handed antiparticles. It's the quantum version of being invited to a party and finding out the bouncer only admits people who twirl in a specific direction. And this isn't just a minor detail, it's the only force we know of that violates parity. In other words, if you created a perfect mirror copy of the universe, the weak force would behave differently in that reflection. All the other forces, gravity, electromagnetism, the strong nuclear force, are perfectly happy being mirrored. But the weak force? Nah, it's got opinions. You zoom in now on a classic experiment from 1956. Two scientists, Qiansheng Wu and her team, set out to prove that nature was not ambidextrous. They used cobalt-60 atoms, lined them up with a magnetic field, and watched how they decayed. And sure enough, electrons shot out preferentially in one direction. A symmetry confirmed. Nature chooses left. Case closed. This was a seismic moment. The symmetry of the universe, long assumed, worshipped even, was now proven to be broken. Handedness mattered. And if nature could break parity, maybe it could also break charge symmetry, preferring matter over antimatter. A crack in one mirror might lead to a crack in another. This wasn't just a physics result, it was a philosophical revelation. Historians still argue whether Wu's experiment should have netted her a Nobel Prize. Spoiler, it should have. But her male colleagues received the honour instead, because science history is sometimes less enlightened than the particles it studies. Anyway, back to the particles. You float now through the bizarre zoo of subatomic entities, and you notice something strange. When neutrinos interact with the weak force, they're always left-handed. Always. Their mirror image counterparts, right-handed neutrinos, don't seem to exist at all. But antineutrinos, they're always right-handed. This bizarre quirk is more than just a cosmic personality trait. It might actually explain the matter, antimatter imbalance. If the weak force has a strong preference for left-handed particles, perhaps it subtly encouraged processes that favoured matter. Even the tiniest bias, repeated over billions of interactions in the early universe, could result in the imbalance we see today. Of course, this is still a theory. The universe, frustratingly, hasn't published its origin story in a peer-reviewed journal. but the chiral nature of weak interactions is one of the most suspicious fingerprints we've found. And then there's the question of mirror matter, a fringe but tantalizing idea. Some theorists propose that for every particle in our universe, there's a mirror particle that lives in a shadow sector. Same mass, opposite handedness. These mirror particles wouldn't interact with regular matter via the usual forces, only gravity. They'd be invisible, undetectable, and possibly responsible for dark matter. If mirror matter exists, it could explain both the matter-antimatter imbalance and the nature of dark matter. Two mysteries, one reflection. But we've yet to detect it. It remains a theory. Beautiful, unconfirmed, and frustratingly quiet. You float back from these quantum spirals and consider what this all means. The universe, your universe, isn't neutral. It plays favourites. It tilts ever so slightly toward one hand. And from that preference, everything else may have followed. Even the weak force's name is misleading. It's weak compared to the strong force, sure, but it's powerful in its asymmetry. It governs beta decay, neutrino interactions, and the mechanisms that may have tipped the early universe toward matter. There's a lovely symmetry in how asymmetry saved us. But just as you're getting cozy with the idea, here's a fringe fact to rattle your mug of anti-coffee. Some physicists have speculated that the entire left-handedness of the weak force might be an illusion. That if we found those elusive right-handed neutrinos, hypothetical particles called sterile neutrinos, the symmetry might be restored at higher energies. Like the universe is only lopsided at our scale, and perfectly balanced somewhere far beyond. Still, that's just another theory, floating out there like a balloon with no string. For now, the weak force continues its asymmetric reign, quietly breaking the rules every time a neutron decays or a neutrino flits through a detector. And we, the lucky benefactors of its bias, exist because of it. So next time you wave your left hand, give it a nod. The universe might be biased toward that side. Or maybe you're just caught in the swirl of particles that chose to spin that way, back before time knew which way was forward. You're in motion again, drawn deeper into the quantum fog following a trail of whispers. Not voices exactly, more like statistical hesitations, fleeting flips, and enigmatic silences. You're closing in on one of the universe's quietest troublemakers, the neutrino. Of all the particles in the standard model, neutrinos are by far the most introverted. They barely interact with anything. You could fire trillions of them straight through a solid block of lead the size of Jupiter, and they'd pass through like ghosts, waving politely, leaving no trace. And yet, they may be the reason you exist. You trail behind one now, a faint blur in the ether, no electric charge, nearly no mass, moving at almost the speed of light. Neutrinos come in three flavours: electron, muon, and tau. But here's the part that makes them not just quirky, but potentially universe-altering. They don't stick to just one flavour. They oscillate. That's right, neutrinos can change identity mid-flight. One moment it's an electron neutrino, the next it's a muon neutrino. These flavour flips were first confirmed in the late 1990s and early 2000s, shocking physicists and winning Nobel Prizes. The reason this is important is simple. If neutrinos can change flavours, they must have mass. Not much, less than a millionth that of an electron, but not zero. And that, dear listener, breaks the original version of the standard model. And more importantly, it opens a door labelled leptogenesis. Here's the idea. In the early universe, right after the Big Bang, there might have been a process involving neutrinos, specifically heavy right-handed neutrinos, ones we've never observed but theorise existed. These neutrinos would have decayed in a way that slightly favoured matter over antimatter. Not by a lot, just enough. It's like the early universe handed out raffle tickets to matter and antimatter, but tilted the bin ever so slightly. After the drawing, only matter got to stay for the after party. This process, leptogenesis, could have created an initial asymmetry in the number of leptons, the particle family that includes electrons and neutrinos. That lepton asymmetry would then have been converted into a baryon asymmetry, tipping the scales toward more protons and neutrons, and ultimately toward stars, planets, and you. The key villain hero in this story? The Majorana neutrino, a hypothetical type of neutrino that is its own antiparticle. Think about that for a second. Most particles and antiparticles are distinct. Electron versus positron, proton versus antiproton. But a Majorana neutrino, it's like a mirror staring back at itself, identical, uncomfortably so. If neutrinos are Majorana particles, they could allow for a rare process called neutrinoless double beta decay, a nuclear reaction that violates the conservation of lepton number. This would be direct evidence that neutrinos are their own antiparticles, and that they might have helped cause the matter-antimatter imbalance in the first place. Right now, dozens of experiments around the world are trying to detect this very thing. From Gerda in Italy to Quarry and Camland Zen in Japan, researchers are waiting for a signal, an event where two neutrons in an atomic nucleus decay into two protons and two electrons, and no neutrinos. It's a tiny, silent moment. But if we find it, boom, evidence that the rules aren't quite what we thought. That symmetry has cracks. That neutrinos, those ghostly shapeshifters, may have saved the universe from obliterating itself in a perfect burst of gamma light. Historians, well, maybe future historians, will definitely argue whether the discovery of neutrinoless double beta decay should count as the single most important experiment of the 21st century. Because if confirmed, it could answer the deepest question we've been asking. Why are we here, and not a puff of photons? And yet, neutrinos don't make this easy. You drift past the Ice Cube Neutrino Observatory, buried beneath the Antarctic ice. It's a cubic kilometre of ultra-pure frozen silence, rigged with detectors to catch the faint flashes of light emitted when a rare neutrino finally interacts with an atom. These events are so uncommon, you can go days without seeing anything meaningful. But we keep watching, because in those flickers there might be secrets older than galaxies. Now here's a slightly fringe but fascinating idea: CPT symmetry violation through neutrinos. Some theorists suggest that if CPT symmetry, charge, parity, time, is ever broken, it might first show up in neutrino behaviour. Maybe neutrinos and antineutrinos don't oscillate the same way. Maybe their masses are slightly different. If true, that would be a cosmic scandal. Not just a nudge in the rules, a full rewrite. The jury's still out. Some early results from Minos and LSND hinted at asymmetries, but later experiments muddied the waters. Welcome to neutrino physics, where every answer breeds two new mysteries and a grant application. You pass through a cluster of data points hovering like fireflies in a server room. Each dot represents a neutrino event, most unremarkable, but occasionally one pulses differently, possibly a hint of that long-theorized sterile neutrino, a fourth flavour that doesn't interact via any of the known forces. If sterile neutrinos exist, they could play a crucial role in matter-antimatter imbalance, dark matter, or both. Of course, they're also invisible, almost impossible to detect, and may or may not exist. So, typical particle physics. And while we're having fun, some speculative theories propose that neutrinos move faster than light. Yes, you read that right. A 2011 experiment from Opera briefly made headlines for reporting such a result, only for it to be later traced back to a loose cable. Still, you have to appreciate the poetic possibility that the quietest particle in the universe might also be the fastest, racing ahead of the light itself, carrying secrets we haven't caught up to yet. You float now, weightless and reflective, surrounded by a soft hum of flavour transitions and possibility. Neutrinos, it turns out, might hold more keys than any other particle. They could be the source of the imbalance, the ghost in the symmetry, the little rebels that chose not to cancel out. They're shy, yes, quiet, but make no mistake, they may have screamed first. You're hovering now at the intersection of order and disobedience, where the universe's clean equations get a little sloppy, and the rules you thought were sacred turn out to be guidelines at best. You're about to witness a tiny rebellion, the kind that whispers across decades of physics and possibly explains how everything around you, your chair, your breath, your third snack of the evening, got here at all. Welcome to the wild and oddly polite world of CP violation. Again. This time starring one of the universe's shadiest little troublemakers, the Kaon. Let's rewind to 1964, You hover beside a particle accelerator at Brookhaven National Laboratory. The air smells like coolant and chalkboard dust. Physicists James Cronin and Val Fitch are peering at the aftermath of particle collisions, watching kaons decay. Strange particles that only live a fraction of a second before falling apart into lighter ones. Kaons, to be specific, are mesons, particles made of a quark and an antiquark, and the ones in question are neutral kaons, which means they can oscillate between being matter and antimatter versions of themselves. Basically, they're indecisive, quantum flip-floppers. At first this seems fine, charming even, but then something doesn't add up. Some of these kaons are decaying into two pions when they shouldn't be. According to the standard model, well, the neat and tidy version of it, that decay should have been forbidden if the universe strictly obeyed CP symmetry, that's charge and parity combined. But here they are, cheekily ignoring the rules. This was the first definitive proof of CP violation. The universe actively favouring one outcome over its mirror image counterpart. In this case, the kaon was more likely to decay into particles than its antimatter twin was, and this tiny imbalance changed everything. Because if CP symmetry can be violated, then so can the perfect match between matter and antimatter. This is one of the necessary ingredients in the great cosmic recipe for baryon asymmetry. That 1 in a billion imbalance that let matter win after the Big Bang. You pause beside the kaons, watching them do their forbidden dance. It's a small thing, an angle barely noticeable, like a painting hung slightly crooked in a museum. But that crookedness may have tipped the entire universe in one direction. Now fast forward a few decades to the 2000s. You drift into the Babar experiment at SLAC in California and Bell in Japan. Here, physicists are watching the behaviour of B mesons, another quirky particle made of a bottom quark and an antiquark. And guess what? B mesons also violate CP symmetry. Not as much as kaons, but enough to confirm the universe has a consistent pattern of subtle unfairness. These experiments helped us understand that CP violation wasn't just a rare quirk, it's part of the fabric of particle interactions. So where does that leave us? Well, so far, all the known CP violation comes from particles involving the weak force, like kaons and B mesons. And while it's significant, it still isn't enough. It can't fully explain why the universe contains so much more matter than antimatter. The known violations are too small, like trying to tilt a boulder using a plastic spoon. Historians, yes, them again, still argue whether undiscovered forms of CP violation exist, possibly in processes involving neutrinos or even new particles we haven't detected yet. Some suspect that strong CP violation, a predicted but unobserved asymmetry in quantum chromodynamics, could play a role, though the absence of such violations is what gave birth to another mystery, the axion, a hypothetical particle invented just to clean up the mess. Ah, yes, physics, the art of making up new things to explain why old things don't behave. And here's a lovely fringe theory to swirl around in your sleepy brain. Some researchers believe that CP violation could be time-dependent. That is, the laws of physics themselves might have allowed stronger violations in the early universe, right after the Big Bang, and then those violations gradually weakened over time. If that's true, we're now living in the calm after the storm. The universe was more chaotic in its youth, more willing to bend the rules. Now it's grown up, mostly stable, but still harbouring a few guilty secrets in its particles. You float through a diagram, an intricate web of decay channels, probabilities and symmetry violations, and it hits you. Everything here is built on imperfection. The fact that kaons occasionally forget how to behave, that pions don't show up equally in all frames, that B mesons can't keep their stories straight, that is the reason you exist. The entire universe, from your brain to your bagel, is the result of a cosmic typo. A beautiful, rebellious typo. And it gets even stranger when you realise that CP violation also implies T violation, a violation of time symmetry. That's right. If CP is broken, then time doesn't necessarily work the same forwards and backwards. This isn't just philosophy, it's physics. The universe doesn't run like a reversible film reel, so maybe time itself plays a role in the matter-antimatter imbalance. Maybe the forward arrow of time, the reason you grow older instead of younger, is entangled with the same asymmetries that gave birth to matter. If that doesn't make you blink slowly at the ceiling tonight, I don't know what will. One more oddball tidbit before we ease into the wind down. Did you know that certain experiments have looked into CP violation in charm quarks too? These are even rarer decays, involving demesons, and any deviation could suggest new physics, stuff outside the standard model. These results are still being debated. Some suggest real effects, others might be statistical noise, but the chase continues. Because somewhere in all this mess, among the twirling kaons, flipping neutrinos and stuttering decay chains, might be the exact point where the universe chose to let matter live. You look around now, as though expecting a kaon to wink at you through the void. It doesn't, but it could. And that possibility is enough, so now we slow things down. You've followed the tangled trail of antimatter from its elegant origins to its mysterious absence. You've watched particles dance in defiance of symmetry, and considered the left-handed lean of the universe. You've hovered beside positrons born in bananas, antiprotons trapped in labs, and kaons caught in the act of betrayal. It's time to let the questions rest, for now. Let your thoughts drift like neutrinos through Antarctic ice. Let the mysteries fold into soft darkness. Whatever broke the symmetry of the early universe, whatever quiet decision tilted the cosmic scales, it left just enough behind for stars, breath, memory, and this moment. So close your eyes. Let the hum of distant particles and the flutter of improbable survival lull you. You're made from the matter that stayed behind. You're the residue of imbalance, and that's exactly what makes you real. You're back now, not all the way awake, but drifting gently through a brighter corridor of thought. The hum of accelerators still pulsing in your ears like a lullaby wrapped in tungsten coils. Around you, gleaming machines extend into the dark like cathedral spires, their purpose singular and sacred, to trap antimatter, to hold the unholdable, to weigh ghosts. This is where science gets poetic. You're floating through CERN, nestled beneath the French-Swiss border, where protons scream around a 27-kilometre underground ring, and teams of physicists dream of symmetrical truths. But tonight, your destination is smaller, quieter, more precise. The Alpha experiment. That's anti-hydrogen laser physics apparatus, for those of you keeping acronym score. Its mission? To create and trap anti-hydrogen atoms long enough to actually study them. Not just detect their brief glow before annihilation, but watch them, hold them, learn from them. You glide into the vacuum chamber, where a forest of magnetic fields hums invisibly, suspending neutral anti-hydrogen atoms in mid-air like microscopic acrobats. They can't touch the walls. If they do, annihilation. Poof. End of experiment. So they hover, held in a kind of magnetic hammock, cooled and cradled by some of the most sensitive instruments ever built. The stakes? Everything. Because if antimatter and matter are truly symmetrical, anti-hydrogen should behave exactly like hydrogen. Same spectral lines, same energy levels, same gravitational behaviour. But if there's even the tiniest deviation, then the laws of physics might be incomplete. You drift beside one of the trapped anti-atoms now. It's mind-blowing that this is even possible. Anti-hydrogen is a neutral particle, a positron orbiting an antiproton, and neutral particles are hard to trap with magnets. But Alpha pulls it off using a clever combination of magnetic minimum traps and cryogenic cooling. The result? Anti-hydrogen atoms held for minutes, an eternity in antimatter terms, long enough to poke them with lasers, to see how they react, to compare their light with that of regular hydrogen, atom for atom. You peek at the results. In 2016, Alpha performed the first ever spectroscopy of antihydrogen, measuring its response to light. The anti-atoms were exposed to lasers tuned to match the frequencies that excite regular hydrogen atoms. The result? A match. Identical. No measurable difference. And in science, a match isn't boring. It's terrifyingly beautiful. Because it means CPT symmetry might still hold true. That antimatter, despite its explosive tendencies, is just as real, stable, and structured as matter. A perfect twin. Until they touch. You spin gently toward Alpha 2, an upgraded version of the experiment with even finer lasers, colder traps, and more precision. This machine isn't content with identical, it wants decimals. It wants to probe the 1 in a billion chance that antimatter is just slightly off. Because if there's an asymmetry to be found, this is where it would hide. Nearby, another experiment hums along. BASE, the baryon-antibaryon symmetry experiment. BASE doesn't use antihydrogen. It focuses on antiprotons themselves, comparing their charge-to-mass ratio with that of protons to astonishing accuracy. And it keeps finding the same thing. No difference. You might think this would disappoint physicists. It doesn't. Every confirmation pushes the standard model's predictions further. Every match tightens the noose around new physics, and every decimal matters. But still, they're hoping. Somewhere in this delicate ballet of opposites, they hope for a mistake, a crack, a subtle, undeniable signal that the universe doesn't treat matter and antimatter equally. That would mean something broke early on, and that break might explain everything. You drift now toward a quieter station, AEGIS, another CERN experiment with an even more ambitious goal. AEGIS wants to answer a deceptively simple question. Does antimatter fall? Yes, fall. As in, does gravity pull on antimatter the same way it does matter? You'd think we'd know this by now, but we don't. Gravity is incredibly weak compared to the other forces. So weak that measuring it on something as delicate as a neutral anti-atom is like trying to weigh a bubble during a breeze. AEGIS uses pulsed positron beams to create antihydrogen, then launches those atoms horizontally, allowing gravity to pull them downward over time. The aim is to measure the vertical displacement, tiny fractions of a millimeter, that would prove whether antimatter falls down just like everything else. A strange, persistent fringe theory suggests antimatter might fall up, that it has negative gravitational mass. If that were true, it could flip our understanding of dark energy, cosmic inflation, even the fate of the universe. Most physicists don't believe antimatter falls up, but they'd love to be wrong. Meanwhile, another team, GBAR, Gravitational Behavior of Antihydrogen at Rest, is working on the same problem. Their approach is different. They aim to cool antihydrogen to almost absolute zero, essentially freezing it in time before dropping it and watching how gravity acts. It's slow, complex work, full of silent victories and particle deaths, and still, not one of them has quit. Because this is how science works when it edges up against the unknown, with patience, with magnet coils, with cooling lasers and a deep, existential curiosity about why we're made of something, not nothing. You float above one of the containment traps now, its magnetic field swirling like invisible armor. Inside, an antiproton pulses gently in silence. It wants nothing. It has no agenda. But its very existence carries the weight of cosmic mystery. What happened after the Big Bang? What made this antiproton one of the losers in the greatest matter-antimatter rivalry of all time? Why did the others vanish? And why did anything remain? Your eyes close for a moment as you consider the scale. Billions upon billions of annihilations in that first second of cosmic history. An entire universe of potential, wiped away in the name of balance. And then, somehow, imbalance snuck in. A 1 in a billion surplus, a mistake, a miracle, or a mechanism. These traps, these labs, these experiments, all trying to catch a single clue hiding in the mirror. And here you are, listening, waiting, drifting through a corridor of anti-stars that never formed and a history that almost didn't happen. The antihydrogen flickers in the trap. The universe leans in just a little, still balanced, still biased, still holding its secrets in the tiniest opposites. Now you're hovering over a scale, not the bathroom kind, thankfully, but a cosmic balance. On one side sits a proton, on the other, an antiproton, identical in mass, opposite in charge. The universe, ever obsessed with symmetry, insists these weights should match exactly. But today we ask something different, a question that's been quietly haunting physicists for decades, despite its childlike phrasing. Does antimatter fall the same way matter does? You float down into the heart of a vacuum chamber, deep inside a lab where gravitational forces are measured in microns and patience is measured in decades. This is the realm of the Alpha G experiment at CERN, an offshoot of the same team that traps antihydrogen. But now they're doing something different. They're not just looking at it, they're dropping it. Imagine suspending an atom of antihydrogen in a magnetic field, then slowly switching off the trap so it begins to fall. Not in a dramatic, cartoonish way. We're talking fractions of a millimetre per second, under gravity's faint tug. Now imagine doing this in an environment where even a whisper of thermal energy would ruin everything. Where a collision with a single stray atom would mean instant annihilation. This is what Alpha G is trying to measure, the tiniest of falls by the rarest of atoms, watched by the most nervous scientists on Earth. And the results? In 2023, the Alpha G team finally released preliminary findings. The antihydrogen fell down, just like regular hydrogen. No reverse levitation, no cosmic joke, no upside-down physics. The whole particle physics community exhaled at once. Except, there's a catch. The measurement wasn't very precise, not yet. They can say that antihydrogen doesn't fall up, but exactly how it falls is still open. Does it accelerate downward at the same rate, or just close? Even a 0.1% difference would be revolutionary. So the experiments continue. More anti-atoms, better cooling, sharper sensors. You drift now into the chambers of G-Bar, another CERN-based project. Their strategy is different. Instead of just dropping antihydrogen, they want to cool it to near absolute zero first. That way, thermal jiggling doesn't interfere with gravity's gentle nudge. GBAR plans to use laser cooling, firing perfectly tuned photons at antihydrogen atoms to slow them down until they're practically still. Then, once an atom is barely moving, they'll let it go and see what gravity does. It's a beautiful idea. Drop a whisper, listen for an echo, and here's the wild part. If antimatter falls differently than matter, even by the tiniest fraction, it could suggest new physics. We might be looking at a crack in Einstein's equivalence principle, one of the cornerstones of general relativity, the idea that all objects, regardless of mass or composition, fall the same way in a gravitational field. Violation of this principle would mean gravity behaves differently depending on a particle's internal structure. And if antimatter interacts with gravity differently, it could explain why it vanished. Maybe gravity itself had a say in the matter, antimatter imbalance. Maybe it nudged antimatter away, literally pushed it out of our visible universe during cosmic inflation. Historians, physicists, still argue whether this idea has any legs. Some theories involving quantum gravity, string theory, or hidden dimensions leave open the possibility that gravity treats antimatter with mild disdain. Fringe, yes, but deliciously tempting. You drift past the blackboard of an ambitious theorist. Equations stretch across it like constellations, swirling with ideas of anti-gravity and gravitational dipoles. One model suggests that antimatter has negative gravitational mass, meaning not only does it fall up, it would repel matter. If true, this could explain both the missing antimatter and dark energy. But these ideas live on the edges of respectability, like uninvited guests at a physics conference. No one throws them out, but no one shares the podium either. Still, you float on. Here's a quirky historical side note. In the 1990s, NASA briefly considered using antimatter as propulsion, and the gravitational behavior of antimatter became part of the discussion. If antimatter could be made to fall differently, perhaps it could even be used to manipulate gravity, a sci-fi notion that still pops up now and then in obscure propulsion patents and YouTube rabbit holes. And just for fun, there's that persistent internet theory that antimatter, when dropped on Earth, doesn't annihilate immediately because it bounces off the gravitational field. No, really, it's not true, but people love the idea of physics having secret exceptions. Back to reality, most evidence so far supports the idea that gravity treats matter and antimatter equally, that they both fall quietly and compliantly toward the Earth, hand in hand until one of them touches the lab wall and explodes. But we won't stop measuring. Because a tiny deviation, one statistically significant wiggle, could upend everything from general relativity to quantum field theory. You return now to the scale. On one side, a hydrogen atom. On the other, its antimatter twin. They sit there, perfectly balanced, as all things should be. But gravity might be keeping secrets. It's the only force that hasn't been fully reconciled with quantum mechanics. It's the softest voice in the standard model choir, and perhaps the one whispering the truth. You close your eyes and imagine it. A universe where antimatter gently floats upward, like a cosmic balloon. Or where, at the dawn of time, gravity bent the rules just enough to send matter downward into stability, and antimatter upward into oblivion. It's speculative, it's delicate, but that's physics at its best. You watch the anti-atom fall one last time, still no bounce, no rebellion, but the scale tips slightly in your mind, and you can't help but wonder, maybe something tilted it first. You're drifting now not through a lab or a particle trap, but through something strangely familiar. Your own backyard, maybe a grocery store, a summer field under a thundercloud, the kind of places where you'd never expect to bump into antimatter. But here's the truth, you do. Antimatter isn't just born in the violent collisions of particle accelerators or deep space gamma ray bursts. It also appears in nature, on Earth no less. Quietly, subtly, sometimes hilariously, like a VIP guest sneaking into a local bingo night. Let's start with something you might have eaten today, a banana. Yes, your potassium-rich snack is radioactive, not in a mutant superpower way, but in a quiet, natural way thanks to potassium-40, a naturally occurring isotope. As it decays, it sometimes emits positrons, the antimatter version of electrons. It's not dangerous. Your body handles it fine. But here's the fun part. On average, a banana emits about 1 positron every 75 minutes. It's like a tiny antimatter bubble machine. If you had a truckload of bananas, and frankly why not, you'd technically be sitting on a natural positron emitter, the world's most delicious reactor. Of course, those positrons don't last long. They quickly find an electron and boom, annihilation, releasing gamma rays. So yes, a banana emits tiny flashes of light you'll never see. Every time you eat one, you become a tiny site of antimatter destruction. Congrats. Now, zoom out to something a little louder than bananas, thunderstorms. For decades, lightning was seen as just electricity and heat. But in the early 2000s, scientists began detecting terrestrial gamma ray flashes, intense bursts of gamma radiation coming from above thunderstorms. At first it was baffling. Where was this high-energy light coming from? The answer? Lightning bolts were powerful enough to accelerate electrons to near light speed, which then collided with air molecules and produced gamma rays. And in some cases, those gamma rays had enough energy to create particle-antiparticle pairs, including positrons. That's right, lightning can generate antimatter. You hover now in the upper atmosphere during a thunderstorm. It's not just water and static up here, it's a natural particle accelerator. Flashes of lightning send electrons careening through air, and when they slam into nitrogen or oxygen, they spawn gamma photons energetic enough to create electron-positron pairs. These positrons can then travel downward, caught in Earth's magnetic field, creating short-lived positron beams that actually shoot down toward the surface before annihilating. It's like the sky is having a surprise antimatter party, and no one thought to tell the weatherman. You shift now towards something quieter, the Earth's upper atmosphere, where cosmic rays from deep space constantly pummel our planet. These cosmic rays, mostly protons travelling at insane speeds, collide with atoms in the atmosphere, triggering particle showers. Among the mess, pions, which decay into muons, which can then decay into electrons and, you guessed it, positrons. So every second, high above your head, there's a mist of antimatter drifting down toward the surface, born from cosmic rays colliding with our protective blanket of air. Most of these particles die on the way down, annihilating or decaying harmlessly. But some actually reach the ground, some even pass through you. In fact, muons, those ghostly relatives of electrons, are constantly flying through your body. Roughly 10,000 muons per square meter per minute pass through you, including the ones that were once part of an antimatter pair. You're more of a particle detector than you ever realised. But wait, it gets even weirder. In 2017, astronomers made a shocking discovery. Using NASA's Fermi Gamma Ray Space Telescope, they observed antimatter signatures above tropical thunderstorms, specifically 511 kiloelectron-volts gamma rays, the calling card of positron annihilation. That meant positrons weren't just being created in these storms, they were being launched upward, into space. In some cases, these positron beams extended hundreds of kilometers above the cloud layer. It's like the Earth was leaking antimatter into orbit. That's not just quirky, it's profound, because it suggests Earth itself might be producing antimatter at rates we underestimated. Not enough to fuel a spaceship, but enough to make physicists raise both eyebrows and double-check the math. You hover now in a hospital hallway beside a PET scanner. That's positron emission tomography. It's a real-world use of antimatter happening thousands of times a day. A radioactive tracer is injected into the body, which emits positrons. These positrons annihilate with electrons in your tissues, releasing pairs of gamma photons in opposite directions. The machine detects those photons and builds a 3D image of what's going on inside. So yes, medical imaging is powered by particle annihilation. Your body, when scanned, briefly becomes a controlled zone of matter-antimatter interaction. And here's another delicious nugget. The human body emits positrons as part of natural metabolic processes involving potassium. You, yes, you, are a source of antimatter, not enough to be useful, but enough to be fascinating. There's even speculation that some animals, like electric eels or other bioelectric species, might inadvertently create conditions conducive to positron production. It's still speculative, but it makes you look at thunderstorms and junglefish a little differently. Historians, physicists, still argue whether the positrons we detect near thunderstorms and volcanoes are produced directly by electrical discharges or by secondary processes triggered by cosmic rays and intense fields. But no one debates that it's real. Antimatter, casually appearing in places that don't even have Wi-Fi. And so, you float gently through this new landscape, one where antimatter isn't just a rare lab specimen, but a recurring character in nature's script. It appears in fruit, in lightning, in your bloodstream. It shows up, causes a scene, then vanishes in a blaze of gamma light. It's humbling. The greatest mystery of existence, why there's more matter than antimatter, intertwined with the banana in your kitchen and the storm on your doorstep. So next time you hear thunder, pause a second. Maybe the clouds are doing a little physics. Maybe the sky is trying to tell you that antimatter never really left. It just lives quietly, right beside you, waiting for the next flash. You're floating now beyond the clouds, beyond banana peels and hospital scanners, drifting into the soft, distant backdrop of the universe's earliest whispers. Not the screaming plasma soup of the Big Bang, but its afterglow, the quiet radiation left behind, stretched and cooled over billions of years. This is the cosmic microwave background, the CMB. It wraps the universe like a baby blanket. A perfect photo of what the cosmos looked like when it was just 380,000 years old. The first time light could move freely, no longer scattered by hot, dense particles. That light has been travelling ever since, cooling as space expands, now visible only to sensitive microwave telescopes. But here's what you're really looking for tonight. Missing antimatter, and the CMB? It's suspiciously silent on the matter. If antimatter existed in significant regions of the early universe, galaxies, stars, even tiny clumps, then boundaries between matter and antimatter would have been violently obvious. Where matter and antimatter meet, they annihilate. That produces huge amounts of gamma radiation, far more energetic than the gentle microwaves of the CMB. So, what do scientists see when they look at the CMB? Smoothness. Ridiculous, frustrating smoothness. No annihilation scars, no glowing gamma seams, just temperature fluctuations at the 1 part in 100,000 level. A whisper of density ripples, nothing that screams mass antimatter genocide. Which leads to the uncomfortable implication. Maybe there was no significant antimatter left by the time the CMB formed. But still, what if we've missed something? You drift past satellites like WMAP and Planck, each having mapped the CMB with increasing precision. They measured its temperature, its polarization, its tiny imperfections. And with each new dataset, the possibility of hidden antimatter gets harder to justify, yet not impossible. Here's where things get interesting and speculative. Some theorists suggest that domains of antimatter could exist beyond our cosmic horizon. That is, far enough away that light from those regions hasn't had time to reach us since the beginning of the universe. Thanks to the expansion of space, there are parts of the cosmos forever out of reach. And if inflation, the rapid ballooning of space in the first tiny sliver of a second, was patchy or uneven, it could have created pockets where antimatter dominated instead of matter. In other words, antimatter universes, separated from ours by billions of light years and expanding faster than we could ever catch up. You can't see them, you'll never reach them, but they might be out there, self-contained, symmetric, distant beyond comprehension. Even within our observable universe, some scientists have tried to sneak antimatter back into the narrative by proposing that there might still be clumps of antimatter hiding in dark corners of space. Maybe anti-stars orbiting at the fringes of galaxies. Maybe even rogue anti-planets wandering the interstellar medium, long since separated from their parent systems. But again, if those objects exist, they're doing an exceptional job of not touching anything made of matter. Because if they did, instant gamma fireworks, and we're watching for those, constantly. The Integral satellite, for example, scans for 511 kilo-electron volts gamma rays, the exact energy signature given off when a positron annihilates with an electron. It has detected that glow, mostly from the centre of the Milky Way, and nobody is quite sure why. Some think it's due to decaying isotopes from massive stars, others suggest dark matter interactions. A few quietly wonder whether tiny antimatter pockets might be hiding in the galactic core, releasing positrons in short-lived spurts. Historians, well, astrophysicists, still argue whether these positrons are from known astrophysical sources or something stranger. But so far, no one's found a definitive antimatter smoking gun. You drift now beside a strange equation, one used in baryogenesis models, attempting to describe how matter could have outlasted antimatter after the Big Bang. Every version of this theory needs something more than the standard model offers. New physics, extra particles, more CP violation, and occasionally just a little prayer. One version, called spontaneous baryogenesis, suggests that a scalar field permeated the early universe and broke symmetry locally, favouring matter in some regions and antimatter in others. This could, in theory, create domains, vast cosmic regions made of one type or the other. But then, of course, we circle back to the CMB. If those domains existed within our visible universe, we'd expect to see annihilation signals at their boundaries, maybe faint, maybe ancient, but real, and yet nothing. So where are they? You float into the realm of dark matter, that ever-present mystery that outweighs visible matter 5 to 1, and which we still can't identify. Some have wondered whether antimatter dark matter might exist, strange antiparticles that don't annihilate because they only interact through gravity. Maybe dark matter is mirror matter, a whole anti-sector, silent and invisible, occupying the same space as us but never touching. It's a long shot. But weirder things have happened, like everything. Then there's the truly fringe possibility that the entire universe is a fluctuation, a statistical hiccup in a larger multiverse where most regions are perfectly balanced and annihilate themselves into gamma ash. But ours just happened to roll the matter dice a few more times. A cosmological lottery win, 1 in a trillion odds paid out in atoms, is unsatisfying, sure, but it matches the data, and in science that still counts for something. So you sit quietly in the void, eyes on the microwave background. You try to imagine what it would look like if a single antimatter galaxy had survived. Would there be a hotspot? A shadow? A ripple? Would we see it? Maybe not. Maybe the anti-domains, if they exist, are tucked away in the margins, sealed off by inflation, unreachable forever. Maybe the story of antimatter didn't end in a bang, but in a quiet exile. And still, the CMB murmurs its ancient light. No gamma tears, no glowing fault lines, just the gentle echo of a universe that chose matter. Or maybe pretends to. Either way, the sky remains smooth, and the antimatter, if it's still out there, is keeping very, very quiet. You're floating through folds now, not of space, not of time, but of something stranger. Symmetry itself. Like a well-tailored suit or a well-planned murder mystery, the laws of physics are built on balance. Flip a particle, reverse a charge, run time backwards, nothing should change. Or so we thought. Tonight, you're going deeper, into the possibility that the universe itself is asymmetric, that it isn't just the particles that are unfair. Maybe space, time, gravity, or even the vacuum between galaxies is tilted. Maybe reality, at its root, plays favourites. You begin with the classic, space-time. Einstein's general relativity tells us that mass and energy warp space-time, creating the effect we call gravity. It's elegant, it's predictive, and it's very, very symmetrical, at least in theory. But maybe not in practice. You hover beside a line of equations scrawled across a chalkboard in a dusty corner of theoretical physics. They describe Lorentz invariance, the idea that the laws of physics are the same no matter where you're standing or how fast you're moving. Now imagine that's not true. A whole class of theories, Lorentz violating theories, propose that there might be preferred directions in space-time, that there's a kind of texture to the vacuum. If that texture interacts differently with matter than antimatter, it could subtly bias the universe from the ground up. In other words, the universe might have a built-in lean, and if so, maybe that lean pushed antimatter out of the picture. Fringe, sure, but not impossible. You drift next into the realm of quantum field theory, where every particle is a ripple in an invisible field. Most of these fields are assumed to be symmetrical, but what if they're not? What if the vacuum expectation values of certain fields favour one type of particle over another? There's a model for this, spontaneous symmetry breaking, where a field that should be neutral chooses a direction, like a pencil balanced on its point falling to one side. That tiny tilt could have made all the difference in the early universe, nudging matter into dominance and antimatter into annihilation. You've heard of the Higgs field, responsible for giving particles mass. It's an example of this exact kind of symmetry breaking, so it's not speculation. It's already happened once. Maybe it happened again, somewhere subtler, somewhere still waiting to be detected. Next, you drift into gravity's house. It's the one force that hasn't been unified with the quantum world, the lone introvert in physics' otherwise friendly group chat. And that makes it suspicious. Some theorists think gravity might hold the key to the antimatter imbalance. Maybe antimatter gravitates differently, not just in acceleration, but in how it curves space-time. If that's true, then even the geometry of the universe would be skewed in favour of matter. There's a concept called gravitational asymmetry, in which gravity might interact with matter and antimatter through slightly different coupling constants. If such a violation exists, it could have influenced the distribution of energy in the early universe, enough to let matter win the cosmic coin toss. But of course, we haven't observed that. Not yet. Gravity is too weak, too slippery, too polite to reveal its biases easily. Still, you can't help but feel that the fabric of space-time is hiding something. Some tiny imbalance buried so deep it would take a universe-sized microscope to see. And speaking of the universe, let's talk about time. Everyone loves time. We're addicted to it. But time, it turns out, is a huge suspect in this mystery. Because while most physical laws are time-symmetric, they don't care if time runs forward or backward. The actual universe most definitely does. Eggs break. They don't unbreak. You age. You don't unage. Stars explode. Galaxies drift. Entropy increases. Always forward. Always into disorder. That forward march of time, it's called the arrow of time, and no one really knows why it exists. One theory? CP violation and T violation are linked. Remember, if charge and parity symmetry are violated, time symmetry is also violated. So maybe the same mechanism that led to the matter-antimatter imbalance also created directionality in time itself. In that case, time doesn't just run forward, it runs toward matter. Some cosmological models even propose that there may be a mirror universe, expanding backward in time from the Big Bang. In that universe, antimatter dominates, and time flows the other way. Two universes, one made of matter and forward time, the other of antimatter and backward time, born from the same event, drifting away forever, unable to meet. It's poetic, isn't it? You hover now over a strange and beautiful idea. Maybe the reason you don't see antimatter is because you're not facing the right direction in time. But let's get weirder. There are models in string theory and loop quantum gravity that predict topological defects in space-time. Knots, twists, or domain walls, where physical laws change slightly. Some believe that in the earliest moments of the universe, such defects could have formed regions of differing matter, antimatter preference. Maybe we're in a matter domain, but others, far beyond our reach, are made of antimatter. The boundary between these domains might have annihilated early on, leaving only the largest, most isolated regions to survive. And what about the curvature of the universe itself? We think it's flat. But if it's even slightly curved, positively or negatively, it could influence how matter and antimatter evolved across cosmic scales. Certain models suggest curvature could amplify even smaller symmetries during inflation, leading to the dominance of one type of particle over the other. So yes, maybe the shape of the universe picked a side. Historians, yes, we're still doing this, still debate whether the symmetry-breaking events that occurred in the early universe were truly spontaneous, or if they were seeded by deeper asymmetries in the laws of physics themselves. Maybe nature isn't fair, maybe it never was, maybe it always leans just slightly toward survival, just slightly toward you. You drift now through the invisible currents of a universe tilted ever so gently toward existence, toward matter, toward the improbable physics that allowed you to hear this story and wonder what could have been. The asymmetries are small, minuscule, but they add up. A particle decay here, a neutrino preference there, a ripple in space-time, a lean in gravity, and suddenly, instead of nothing, there's everything. A universe that should have vanished in a flash of perfect balance, but didn't. Now you're drifting straight into the math, not the sleepy bedtime kind, the real, scribbled on a napkin by a genius kind. The sort of math that bends time, flips charge, and dares to imagine what antimatter actually is. Because what if we've been thinking about this backward? Literally. Tonight you glide into the elegant chaos of Feynman diagrams, those friendly squiggles that physicists use to represent how particles interact. To the untrained eye, they look like simple line drawings, arrows, loops, wiggles. But inside those loops, the soul of the universe. You hover beside one now. A wavy line representing a photon connects a straight arrow pointing forward, an electron, to another arrow pointing backward. Wait, backward? Yes! According to Richard Feynman and the quantum field theory he helped build, an antiparticle can be interpreted as a particle moving backward in time. It's not just a poetic metaphor, it's baked into the math. In Feynman's framework, a positron isn't just an electron with a positive charge. It's an electron retracing its steps through time. The negative energy solutions of the Dirac equation, the ones people originally dismissed as unphysical, were reinterpreted as real, just with a flipped temporal direction. You pause here. That idea, so small, so absurd, might be one of the most profound things ever proposed. It means every time you create an electron and a positron, you're not making two particles. You're creating one particle with two narratives, one moving forward in time, one moving back. An annihilation, then, isn't just destruction. It's a reunion. A particle meets its time-travelling mirror image, and they cancel out. Not because they die, but because they complete each other. And maybe that's all the universe is. A web of particles crisscrossing through time, some moving forward, some in reverse, all intersecting briefly to make atoms, galaxies toast. You drift beside the ghost of a thought experiment. What if all electrons in the universe are actually the same electron, bouncing back and forth through time, showing up again and again in different places? This was a real idea proposed by physicist John Wheeler, Feynman's mentor. He suggested that there might be only one electron in the entire universe, zipping through time like a quantum ping-pong ball, looping endlessly, appearing as a sea of electrons and positrons depending on which direction it's going. It sounds absurd. It is absurd, but it's not easy to disprove. And anyway, the math lets it live. You tilt now towards CPT symmetry, the crown jewel of quantum field theory. According to this theorem, if you flip charge c, parity p and time t, a particle interaction should look exactly the same, like a cosmic undo button. Flip the charge, particle becomes antiparticle. Flip the parity, mirror image. Flip the time, reverse the action. Do all three, and the universe should still follow the same rules. Neat, tidy, elegant. But here's the uncomfortable truth. If CPT symmetry holds, then antimatter is not optional. It must exist. It's not an invention. It's an inevitable consequence of how time and quantum mechanics get along. So maybe we're not just dealing with a symmetrical universe that got a little messy. Maybe we're looking at a deep structure, one that demands time and matter and antimatter to balance across dimensions we can't even see. You pause beside another Feynman diagram, tracing a loop where a particle emits a photon, absorbs it, and keeps moving. In that loop, time gets fuzzy. The particle isn't just travelling, it's interacting with its own past. And maybe that's all particles ever do. Weave stories through time, bumping into each other's histories, their futures curling backward, their presents colliding. And antimatter, it's the shadow side of that dance. It's not other, it's not wrong, it's just the same stuff facing the opposite way. Of course, not everyone agrees on what these time-flipped interpretations mean. Historians, yes, physicists again, still argue whether antimatter literally moves backward in time, or whether it's just a trick of the math. The diagrams work, the equations balance, but whether particles experience time in reverse, well, what does it even mean for a particle to experience anything? But here's a tasty fringe theory to stir into your tea. What if the direction of time is relative? Just as motion can only be measured relative to something else, maybe time's direction isn't fixed either. Maybe to an antiproton you're the one moving backward. In that case, the Big Bang wouldn't be a single beginning, but a point of divergence. Two universes splitting outward in opposite temporal directions, each filled with their own dominant particles, one with matter, one with antimatter, each thinking they're moving forward. This could even explain the apparent lack of antimatter. It's not gone, it's simply receding from us in reverse. You drift further, toward the speculative shores of retrocausality, where some physicists suggest that particles can influence past events. The equations of quantum mechanics don't forbid it. In fact, they often behave as if time is symmetric, with outcomes shaped by both the initial and final conditions. Could antimatter be a signature of that? A sign that the future is leaning back to nudge the past? We don't know, but the implications are dizzying. You pause for a moment, letting the diagrams fade. You think about a positron being created in a particle collision, flying forward, or perhaps backward. You think about a universe where the same particle dances through space-time, sometimes advancing, sometimes rewinding like a looped dream. You think about time not as a river but as a web, and every antiparticle, just a thread running the other way. The more we study antimatter, the more it refuses to stay in its lane. It's not just matter with the signs flipped. It's a window into something deeper, something fundamental about time, about symmetry, about the hidden directions of the universe. And maybe that's the real reason it vanished. Not because it lost, but because it left. Backwards. You're nearing the edge now, not of the universe, not of understanding, but of the story itself. One that began with perfect symmetry, spiraled into imbalance, and left behind only the faintest fingerprints of what should have been. The final traces of antimatter. You drift now beyond laboratories and lightning storms, past kaons and cold traps and banana peels. Here, you meet the silence left behind by absence, a universe where matter rules, quietly, persistently, unfairly. But before we fade completely, there's one last place to visit. Not a lab or a telescope, but a future, a collection of possibilities, the places we're still searching, and the strange ideas that might someday rewrite this whole tale again. Let's start with something active, a MS-02. That's the Alpha Magnetic Spectrometer currently perched on the International Space Station. It's been quietly orbiting Earth since 2011, scanning cosmic rays for something extraordinary, antimatter nuclei. Yes, nuclei. Not just lonely positrons and antiprotons, which are relatively common in cosmic rays, but heavier antimatter, anti-helium, even anti-carbon. Something that would prove there are whole structures of antimatter out there. Not just specks, not just traces, anti-stars, anti-galaxies. MS-02 has recorded several intriguing candidate events, blips in the data that might be anti-helium, but none confirmed yet. The challenge is enormous. Out of billions of detections, you're looking for one unmistakable wrong-way nucleus, like trying to find a single reversed letter in a global library. But if confirmed, that would be it. Proof. You'd know that somewhere out there, antimatter still thrives, that it didn't vanish, just retreated, tucked away in quiet corners of the cosmos, building its own chemistry, its own suns. The implications would be cosmic. And so the search continues, not just with AMS-02, but with future missions like GAPS and HERD, designed to scan even more cosmic rays, more deeply, more cleanly, in the hope that one rogue nucleus might finally break the silence. You float now through the quiet ambition of proposed future colliders. The Future Circular Collider, a potential 100-kilometre ring of power beneath Europe, would allow for unprecedented particle collisions, billions of opportunities to spot rare decays, new CP violations, or perhaps even new particles that hint at why the symmetry broke in the first place. Because here's the thing, the standard model, as powerful and predictive as it is, doesn't cut it. It can't explain the imbalance. It has some CP violations, yes, but not enough. It doesn't account for dark matter or neutrino masses, or why the universe didn't immediately self-annihilate. That's why physicists chase supersymmetry, leptogenesis, sterile neutrinos, axions, mirror universes, and a dozen other exotic options. Not because they're wild guesses, but because the current model is too tame to explain this cosmic crime scene. Historians, physicists again, still argue whether new physics lies just out of reach of our machines, or if it's hiding in a place we haven't even thought to look. Maybe we've been asking the wrong question all along. Instead of, where is the antimatter? Maybe we should ask, why is there matter at all? Because here's the twist. In a perfectly balanced Big Bang, matter and antimatter would have annihilated completely. No galaxies, no stars, no you. The universe would be a smooth bath of light, cooling forever, devoid of structure. That didn't happen. Something broke the symmetry. Something leaned just slightly. A subtle, deliberate unfairness. And that unfairness made everything. So maybe the universe isn't fair, but maybe it never needed to be. You pause now at the edge of one final thought. A possibility, a hope. What if we do find antimatter galaxies someday? What if we spot a star drifting alone at the edge of the void that glows with gamma light from boundary annihilation, where its antiprotons meet the occasional rogue hydrogen atom from the intergalactic medium? What if we discover that the universe was never entirely one-sided, just segregated? And what if, in time, matter and antimatter meet again, peacefully or otherwise? Would we welcome it? Or would we call it danger? We don't know, but we'll keep looking. Because somewhere out there, hidden in thunderclouds, drifting through cosmic rays, flickering inside particle traps or riding time backward, might be the final piece of the puzzle. And when we find it, we might not just explain the universe, we might understand why it exists at all. Because for all the symmetry we love in physics, it's asymmetry that gave us stars, it's imperfection that gave us light, and it's the loss of antimatter that gave us everything else. Now, just ease back. The questions can rest for tonight. The neutrinos can stop oscillating, the positrons can stop flashing through banana peels and thunderstorms, and the Big Bang can sit quietly in the rear view. Let it all drift. You're floating through a universe sculpted by silence, by the quiet absence of a twin that should have been, a ghost that never made it past the first second. And somehow, in that tiny imbalance, in a universe that favoured one over the other, something bloomed. Stars, chemistry, breath, you. There's peace in knowing that perfection isn't necessary, that balance isn't the rule, but the exception that almost was. That existence, yours included, is the residue of a tiny cosmic preference that no particle has explained. Let that comfort you. Let the thought of time-flipped particles and left-handed forces fade to a soft hum, the kind you hear only in the deepest stillness. You don't need to solve it. You just need to rest in it. So close your eyes and let your breath match the cooling of the early universe, that slow exhale of energy that gave rise to galaxies. Let each inhale carry the weight of protons that never met their match. Let each exhale carry questions that can wait until morning. You're safe in the matter that stayed behind. You're cradled by the symmetry that broke. And somewhere, out in the quiet dark, the antimatter listens, just like you.